Hello everyone, welcome back to my channel. Happy holidays, Merry Christmas, Happy New Year. There's not much time left from this year, so soon we will be in 2024. These are the last videos that I make on this year, so I hope you have a great time during the holidays. In the last few weeks, I have been occupying myself with buying and testing a number of lithium-ion and even lithium iron phosphate accumulators. I bought them from a local market and I wanted to test them because I didn't trust them. I bought them from vendors that had a very weird price for them. And also their specifications were a bit weird, a bit too much, too good to be true. So I'm making this video for you more for inspiration purposes and to show you what kind of tests I've done, what kind of tests make sense to be done, and what kind of calculations we should do in order to establish whether or not a certain accumulator makes sense to be bought, or in order to establish if we even want to buy lithium accumulators or perhaps lead acid accumulators, and basically to give you an overall view on accumulators, when we might want to use them, what kind of limitations we might have, if we have any, and so on and so forth. Even though I will show you all sorts of products bought from a local market that you may or may not find on your market as well, this video is still going to be useful because I am sure that you will have in your country something similar. Okay, so what I will present to you will definitely be of use if you decide, like me, to start creating devices with accumulators inside, such as an uninterruptible power supply, or even if you are into solar power devices, solar power energy systems, and so on and so forth. This video will definitely have something valuable and useful to you. Before we start with everything that I want to show you, and before I thank the sponsor of this video, I just need to put out a little bit of a disclaimer. There have been certain things going on in my personal life, and because of those things I am still affected to a certain degree, and because of that I will tend to speak slower and probably with a little bit more difficulty in this video and in the next videos to follow. So just bear in mind that you can definitely use the speed control of this video. You can just go on the lower right side of your YouTube player and you know, adjust the speed, the playback speed, to make this go faster, because I will definitely probably speak slower than the usual, and I will even perhaps stutter a little bit more than the usual. Like I said, something has happened in my life, not much that I can do about, but yeah, I am still affected. I'm gonna spare you the details because they are personal anyway, and besides the scope of what I do here on this channel. So anyway, let's dive into the subject, but first please allow me to give thanks to the sponsor of this video, which is PCBWay, and give you some pretty good news in the process. If you need help creating PCBs, maybe even assembling them with components, or perhaps building a device that needs a case and you would like that 3D printed or CNC machined, then you can definitely rely on the quality services of PCBWay. And to make things even better, since we are still in the middle of the winter holidays, they are currently offering Christmas big sales discounts up until the end of this year. you might find you can benefit from 50% discounts on ordered PCBs, 3D printed objects or CNC machined ones, free Christmas coupons based on your order size, and they even have a lucky draw where you could just win some goodies by just clicking virtual boxes on the screen and seeing what those virtual boxes hide underneath. Go check out what they have to offer. The links are in the description below. Thank you PCBWay for sponsoring this video. And now let's get started with everything I want to show you about accumulators, when we might want to use them outside of their use cases, of their usual use cases, and most importantly, what we need to test about them to make sure that what we bought makes sense. Okay, so like I said, I have bought and tested a few litiu accumulators. When I say a few, I mean more like 30 pieces in total or something like that. And I've also had a couple of lithium iron accumulators, which are a little bit different. They have a different chemistry inside, lower voltage, theoretically higher reliability. My personal desire is to create UPSs, so-called uninterruptible power supplies, and later to move towards move towards bigger systems like solar panel, energy systems and such. Anyway, let's talk a little bit about choosing an accumulator. And by the way, I have put a small video on loop on the screen, just so that you know, you don't have to stare on a blank desktop wallpaper. I will present this video and the tests that I've done in a moment, when I will make a quick recapitulation of the general theory of the accumulators. Okay, so when we are choosing an accumulator, well, we have a few things to think about. First of all, if we are using an accumulator for a very specific kind of purpose, such as to replace him on our car, or in a UPS that we actually bought, you know, from the market, not one that we manufactured ourselves, or in any situations when we want to replace an existing accumulator, then the choices are much more limited. Based on what we need to buy a new accumulator that fits exactly the criteria of the old accumulator. For example, if you have a car, of course the lead acid accumulator of your car will be a specific size, a specific capacity, so you won't be able to buy pretty much anything else and fit that inside your car. So of course you will be limited in terms of what you should choose. If you have a portable device that uses, I don't know, let's say 18 650 lithium accumulators, then of course you need to replace those with new accumulators that are of the exact same size and the exact same chemistry. The size 18650 and the same chemistry, because you need the same voltage. Okay, you cannot switch to something else because either they won't fit anymore or their voltage will not be good enough. However, when we are designing and creating a device of our own, we no longer have these limitations, so we can potentially choose any accumulator whatsoever. Okay, and we might have different kind of limitations, or we might not have any limitations at all in terms of size, weight, and so on and so forth. So in that moment we need to think about, okay, which accumulator do I choose and why? And there are basically three. Let me put on desktop. There are three kinds of accumulators. Before that, allow me to give another small disclaimer, just so we know, what we're talking about. I'm not super big expert on accumulators. I have learned a lot in the last few months, so I have a general theory that I understand on a decent level, I would say. My practical experience with accumulators is not all that great. Okay, I have accumulated enough to make this video, but I do not want you to take this video as an absolute truth regarding accumulators and everything about accumulators. Okay. Another thing that I need to mention is that the accumulators that I have tested, and I will present to you in a moment, I have bought them from 2 local vendors only. So, of course, they do not represent everything that there is out there on the market. My local market seems to be pretty limited for some odd reason. We don't have that many companies selling accumulators here, especially litiu accumulators. I mean, lead acid accumulators, yeah, there are plenty of them. But litiu accumulators, and especially lithium iron phosphate, well, the market seems to be pretty limited in my country, so yeah, bear that in mind. And on top of that, the theory of accumulators seem to be scattered around various websites, and I cannot say that I could find a central point that tells me everything about accumulators. So I have compiled informations from multiple sources. In this video, I will make some simplifications and sometimes some oversimplifications, just for the sake of giving you the absolute essence of what it means to work with accumulators. If you need to understand more and more in-depth informations, you are highly welcomed to do your own researches on the internet. Okay. So, with that out of the way, let's just make a quick recapitulation of the 3 biggest types of accumulators, at least from my perspective. The so-called lead acid batteries. Okay, they have lead electrodes and sulfuric acid for the electrolyte. Well, it's not pure sulfuric acid, it's a solution of some sulfuric acid, I believe around 30%, I'm not 100% sure, but anyway, these are the absolute oldest kind of accumulators. They have the cheapest price per unit of energy. They are found in many places, such as in most of your cars, in most of the UPSs out there. They are the simplest technology. Like I said, it's one of the oldest ones. Because of the technology being simple, they are also very easy to recycle and to refurbish. Okay, and they don't really require cell balancing. Typically, we don't buy a single cell of a lead acid accumulator. We actually buy an entire battery that has inside of her several cells. A 12-volt battery has actually has 6 cells, because each cell has 2 volts. Okay, and we will always be working with the entire battery of accumulators, not with each individual cells, because they don't really require cell balancing. So as far as we know, we don't even care about each cell individually. So when we will recharge such an accumulator, whatever happens inside is something that we don't care. How each cell managed to recharge herself is not something that we really care, and these are advantages. Okay, now let's mention the disadvantages. Well, since we have electrodes made of lead, then they are very heavy, and they are one of the heaviest metal, right? So overall, these accumulators are a very heavy weight. A truck accumulator can get up to 80 kilograms, and that's 80, not 18. Okay. They have a low depth of discharge, and I will talk about depth of discharge in a moment to explain what that is. A low depth of discharge is not particularly an advantage; it's actually a disadvantage. Okay, and they have a relatively low lifetime, which, needless to say, it's not something that we want. Now, the second kind of accumulators that we can buy from the market are litiu-ion or litiu-polymer. Now, these are actually simplified names. Actually, there are several technologies of litiu-ion accumulators, each having their own name based on whatever chemical substances are put inside. I'm not going to go over everything. Because it doesn't make sense. Now, these are relatively lightweight compared to lead-acid batteries, lead-acid accumulators, okay? They have better depth of discharge than the ones with lead for the same lifetime. However, as disadvantages, of course, they are more expensive than the lead-acid batteries. They are polluting more because the technology is newer and implies even more toxic substances. After all, lithium is not exactly, digestible or friendly with living creatures. And to make matters worse, each lithium accumulator requires cell balancing. So if we are to take multiple cells and place them in a series, then we would have to have what's called a BMS, a battery management system. The same thing if we want to place multiple cells in parallel to increase the overall current, then we need to take care of certain things, like each cell has to have an equal capacity. We cannot put multiple cells of completely different capacities in parallel because that would create a problem, and so on and so forth. So these kinds of accumulators require a bit of headache, to put it this way. When we are working with them, they are more complex, they require a bit more knowledge and work and attention, okay? And the third kind of accumulators are still manufactured with lithium. However, they have a different chemistry on the inside, lithium iron phosphate. They are relatively lightweight, same as lithium-ion compared to lead-acid batteries, okay? They have better depth of discharge than both of the above types of accumulators, and they have an overall bigger lifetime, so a bigger number of cycles of charging and discharging them. Like lithium-ion and lithium-polymer accumulators, they do require cell balancing, and the price is, well, actually, I find nowadays that the price is kind of depending on various factors. It used to be, or at least this is how I remember, that it used to be that these lithium iron phosphate accumulators were really expensive, much more expensive than any other accumulator. However, nowadays, and I will show you in a moment, nowadays I can find them as cheap as some lead-acid batteries, which I honestly cannot explain, but anyway, this is what I found. Now, besides these three kinds of accumulators, there are also a fourth kind that I didn't mention here because I personally don't care about. The nickel cadmium or nickel metal hydride accumulators. Those look like small 1.5 volt batteries. They have 1.2 volt nominal voltage, much lower capacity, and so on and so forth. So overall, personally, I'm not interested in working with those kind of accumulators, okay? This is why I made a comparison between the top three kinds of accumulators, okay? Now, let's move on to a little bit more theory before we can actually see what comparisons I've made, what tests I've made, and before we can, talk about what accumulator is worth buying, which one is overpriced, and so on and so forth. We need to make sure that we know what to calculate in the first place. Because whenever we go on an online shop, okay, we see some characteristics and a certain price. And the same goes for pretty much every accumulator out there on the market. We see some specifications and a certain price, and we need to establish whether or not those are, worth their money or those are too expensive. However, we cannot just simply compare, apples with bananas and strawberries, because they are different things. So first, we need to understand a little bit of the background concepts in order to know what calculations we need to do in order to basically flatten everything so we can compare two accumulators, even if they are radically different. Okay, so we know that the electrical power, notated with the letter P, is voltage multiplied by current, and it's measured in watts. We use the letter double V for that. Okay. In my part of the world, we use letter U for voltage. Just so you know, if you're more like on the western part of the world, you use letter V from voltage. We don't say voltage, we say tension, electrical tension. And in order to make a clear distinction between volts, the measurement unit, and voltage, the measure herself, we use different letters. Okay, just so you know. So power equals the voltage multiplied by current. When we need to express the amount of energy that a battery or an accumulator has inside of him, then we need to express that in terms of how much power we can extract out of that battery or accumulator over time. So energy, which I have chosen to notate here as letter E, is power multiplied by time, therefore voltage multiplied by current multiplied by time. Normally, electrical power is written with the letter double V, and power in energy, not power. Energy is notated with letter double V. However, that makes a bit of a confusion with the double V from watts, from the measurement unit of power, so I have chosen to use letter E instead. I do know that letter E is used for electromotive force, which is not a force, it's a voltage, and yeah, there's an entire rabbit hole there. I'm not going there. Just so you know, I'm using letter E for energy because it's simple. Okay, it's the first letter in the word energy. And because, in the international system of measurement, time is measured in seconds, but 1 second is a bit too small, we use hour in electricity and in electronics. So the measurement of unit for energy is watt hours. Now, sadly, when people manufacture batteries and accumulators, they choose to express their capacity in amp hours instead of watt hours. And this sucks because amp hours is just this part, the current multiplied by time. This makes it very difficult or pretty much impossible to compare two different accumulators of different voltages, because obviously we cannot just compare amp hours with other amp hours. So for the duration of this video, I will convert everything into watt hours. And the idea is very simple. In order to In order to convert the nominal capacity of a battery or of an accumulator, we simply take the amp hour rating written on him, multiply that by the nominal voltage of that accumulator, which is typically also written on him, and that's going to give you the nominal that's going to give us the nominal energy that that accumulator has. However, bear in mind that this is also a simplification. In practice, the voltage of an accumulator varies quite a lot based on how charged that accumulator is. Therefore, in order to know how many watt hours of energy an accumulator has, we really need to just measure that. And this is one of the reasons why in my previous video that I did about a week ago, I showed you how to build and how I built myself a cheap litiu accumulator tester. This is the kind of device that can basically discharge an accumulator and at the same time measure the actual energy inside that accumulator. Anything else is just an approximation. Okay, so you can use such a device or any other device that does the same thing in order to measure the real capacity of an accumulator. Because let's say if we take a lithium or a lithium polymer accumulator, a standard one, then he has a 3.7 volt nominal voltage that actually is somewhere in the middle between the maximum voltage when he is full, 4.2 volts, and the minimum voltage at which we should discharge him, and that is 3 volts. Some people say 2.7, some others say even 2.5. Personally, I'm not a fan of discharging a lithium accumulator lower than 3 volts. So we have a 1.2 volts difference between the maximum and the minimum voltage. Needless to say, that is around 29%. So 1.2 volts referenced to 4.2 means 29% voltage drop between when he is full and when he's empty. And needless to say, this also means a 29% power drop and therefore energy drop, okay, from when he is full to when he is empty. So if we have a load that consumes 1 amp, and let's say the load consumes a constant current of 1 amp, well, when the accumulator is full, that's going to mean 4.2 watts. When the accumulator is empty, that's going to mean 3 watts. And I would say the difference is, significant. To make matters worse, the discharge of the accumulator most of the time is not linear, due to the fact that most often than not a consumer, a load, right, needs a constant voltage on his input, on his power input, and for the most part will consume a constant current. This is why I drew here 2 lines, one with blue that represents voltage, one with red that represents current. However, the accumulator voltage, like I said, is going to vary depending on the state of charge of that accumulator, and therefore we will most likely need to use a power source between the accumulator and the consumer. It's probably going to be a DC-DC converter, either a step-up converter or a buck boost converter, at least if we are using a single cell accumulator, because we need to, we need to take this 3 to 4.2 volts voltage range and step this up to 5, maybe 3.3 volts if we have a digital 3.3 volt circuit as a load. Anyway, as the accumulator depletes himself, the voltage will drop, but in order to maintain the same power delivered to the consumer, the power source will start, the DC-DC converter will need to start drawing more current, okay, which in turn will make the accumulator deplete even faster, which will drop the voltage even more, which will make the power source draw even more current, and so on and so forth until the accumulator is fully depleted. So yeah, from the accumulator perspective, the voltage goes down, but the current keeps going up. And needless to say, this is one of the reasons why, in order to measure the capacity of the accumulator, we really need to be expressing that in watt hour, not in amps hour. Okay. Because the amp hour rating is a bit deceiving, since it sort of implies that we will draw a constant current, and therefore we somehow will be able to easily calculate the time that it takes for the accumulator to get empty. That's not really the case. Anyhow, moving on with the theory, before we, in order to better understand the differences between accumulators and the next experiments that I've done, the next benchmarks or tests that I've done, call them however you want, let's define a little bit the state of charge and depth of discharge and see how those play in the actual accumulators. So the state of charge is basically a percentage that tells us how full that accumulator is, with 100% being full accumulator. So basically an accumulator that perhaps we have charged completely, and right now he stands waiting for a load. 0% state of charge is when the accumulator is completely empty. Okay, we have used him for a load, he has depleted himself completely, and that is 0% state of charge. Sometimes it makes sense to specify the state of charge. Some other times it is easier to express the exact opposite, which is the depth of discharge. Okay, the depth of discharge is, like I said, exactly the opposite. So when the accumulator is completely empty and we can say his state of charge is 0%, this means that we have discharged him 100%. Okay, therefore the depth of discharge is 100%. And when the depth of discharge is 0%, this means that we have not taken any energy from him, therefore the accumulator is full. It's the equivalent of having a state of charge of 100%. Okay? So, to understand how this goes better into each type of accumulator, well, in order to have around 1000 cycles of charging and discharging a lead acid accumulator, we need to have the depth of discharge no longer than 50%, not bigger than 50%. In other words, in order to have a decent lifetime out of a lead acid accumulator, he needs to be kept at he needs to not be discharged more than half of his capacity. This also means that we need to be very aware of how much energy we need to take from our accumulators, and we need to buy accumulators that in total have basically twice or even more the capacity that we actually need in our device, in our circuits, in whatever project we are creating. Okay? Good. Now, when it comes to lithium-ion polymer, the depth of discharge that these kinds of accumulators allow us is a little bit higher. Not much, but they allow us to deplete 60% out of their energy, and we must keep them at around 40% state of charge for the same roughly 1000 cycles of charging and discharging. Of course, these are general values of your personal use case might vary quite a lot, and the best in this chapter is lithium iron phosphate. They say that we can go up to 80% depth of discharge. On certain websites I've even seen 90 or 95%. I don't know, I cannot guarantee. All I'm giving you is the theory here. Okay, So 80% depth of discharge in order to have even more than 1000 cycles of charging and discharging. Of course, this is an advantage because it means that we can almost completely discharge the accumulator, right? So in order to have 100 watts of energy, 100 watts hour of energy for from a lead accumulator, we need to have a 200 watt accumulator. We need to have only 166 watt lithium or lithium polymer accumulator, and we need to only have 125 watt lithium iron phosphate accumulator, okay, for the same 100 watts of energy, of power, of energy, right? So this is pretty much it in terms of the general overview of accumulators. And there's something a little bit more. There's also the internal resistance of an accumulator, which can be the kind of detail that can tell us a little bit about in what state that accumulator is. You know, is that accumulator still good, or has he been used quite a lot? Can he give us a high current? Can he not? Any battery and any accumulator has an internal resistance. It's due to the chemistry inside of him, and that internal resistance is basically a limiting factor that determines how much maximum current we can get from our accumulator and how much of a voltage drop we will experience when we are drawing various currents, okay? Because the internal resistance manifests herself as just like a resistor placed in series with the accumulator or the battery and whatever load we might have on the output, okay? Now, there is a very simple way that we can measure the internal resistance, and we don't need any special device. All we need is a multimeter or a voltmeter and some power resistor that has a known value that we can place in parallel with the accumulator, and we can calculate the internal resistance with this formula, because the internal resistance will then form a voltage divider with the external resistor that we are actually applying. Knowing the external resistor, knowing the voltage without this resistor, so the voltage in the air, if we just place the voltmeter on the accumulator without any kind of load, we will get a reading, and then when we will place this external resistor, we will get a different reading, okay? And by using those measurements in our formula here, we can establish the internal resistance, which is the voltage of the battery, the voltage that we measure with no load whatsoever, multiplied by the external resistance that we will eventually apply here, divided by the measured voltage when we have this external resistor here, so the voltage across this external resistor, and everything subtracted the external resistance value, okay? So this formula will give us the internal resistance of that particular accumulator. And when it comes to second-hand accumulators, we will pretty much always see that the internal resistance will be higher, because them being second-hand means they have been used. Their capacity is lower than what it should be, and yeah. Let me show you, okay, some measurements that I've done to establish the internal resistance of a couple of my own accumulators. So what we see here is that we have 5 ohms for this decade resistor box that I built myself. 5.4 ohms. Well, the wires have some resistance, but anyway, let's say 5 ohms. I am then later switching from resistor to voltmeter. I'm measuring the voltage without a load to this particular accumulator, 3.311 volts. This is a lithium iron phosphate accumulator. Okay, so his voltage was around his nominal voltage. Let's see, let's start to calculate. 3.311 multiplied by 5 divided by the voltage measured with this resistor, which I'm going to connect in a moment, and it's gonna drop. Okay, so let's say 3.283. The voltage will keep dropping. We need to just make a quick measurement here. I've paused this video, but in real life, you know, you will have to take a look at this and just perhaps have a piece of paper and a pen and write this number down. So 3.283 is the one that I'm going to choose. Okay, and we subtract this from we subtract 5, which is the external resistance, from this value, and we get a value of 0.043-ish ohms. So 43 milliohms is the internal resistance of this particular accumulator that I have tested here. Okay, and I will be switching the accumulator with a lithium 18650 accumulator, which is second hand. It has around 2 amp hours, even though it says 5 amp hours on him, but yeah, either he was 5 amp hours and was extensively used before, or wasn't 5 amp hours at all. Anyway, I'm going to be using this to perform another measurement of the internal resistance, just for you to see another example. Okay, we have the same 5 ohms as an external resistance, external load, and I have connected. Okay, so we have 4.22 volts without any load whatsoever, and with the load we have let's say 4.13. okay, so the voltage has dropped, and like I said, she will continue to drop if we keep the load applied. So we just apply the load, take a quick snapshot of the value, and then disconnect the load, especially since the load is a pretty low value resistor, 5 ohms. It's quite low. Okay, so I will choose to say now we have 4.13 volts. So the number before divided by 4.13, and if we extract 5 from this, then we get basically 110 milliohms for this accumulator that I've just shown you. Basically, he has a slightly higher internal resistance than the previous one, and this also shows that he has been used more. He's more of a second-hand accumulator than the previous one. Okay, and this is pretty much it in terms of all the theory that you should know about any accumulator, really. Now, let's dive into the tests that I have made, because yes, I have bought a whole bunch of accumulators from the local market that had a very good price. They were not labeled as second-hand, but they were second-hand, and in some cases they are just not worth it. So now that we understand the concept of you know, watt hours, we need to calculate or measure, preferably measure, the real capacity of our accumulators in order to be able to compare that with other capacities and to calculate the most important thing, which is the price per watt hour for each accumulator that we might want to buy in the future, or we might want to buy more in the future. Okay, before we get into the each individual tests, which like I said have been done from my local market, let's see with what we should be comparing those numbers with. Okay, because I here have a whole bunch of prices per watt hour. They are in my currency, but you can just divide this number by 5 in order to, you know, get the price in dollars or in euros, however you want. It doesn't really matter all that much because, of course, in your country prices will differ. What matters is that you will have to basically redo this research for yourself and see for your local, in your country, for your local market, how prices are. In my country, I have seen that the absolute cheapest higher capacity lead acid accumulator is for some cars that come from Asia and are quite rare around here. They are not very often seen on the streets. And because of that, there are various manufacturers and distributors of lead acid batteries that set a relatively low price for these kinds of, you know, lead acid accumulator. For me, it was this particular lead acid battery, 12 volts, 100 amp hours. That was around $90, 90 euros or so. Anyhow, the exact price doesn't really matter. What matters is if we convert this into price per watt hour, this results in 0.36 lei per watt hours. Like I said, just divide this by 5 in order to get the price in dollars or euros. So it's around 7 cents per watt hour, and this is the absolute cheapest price that I could find in my country, on my local market, per watt hour. Okay, if we ignore everything else and we just think about the price per watt hour, this is the absolute cheapest price. When it comes to other lead acid batteries, if we want smaller ones, like ones for the ones that we need to put into UPS devices, then these will become more expensive for some reason. 12 volt 7.2 amp hours are 0.82 lei, so it's more than double the other kind of lead acid battery. 12 volt 9 amp hours, like the one I've just shown you here, 0.84 lei per watt hour. Okay. Surprisingly, a similar price is for lithium iron phosphate cells. If we take a look at this EVE 280 amp hour lithium iron phosphate, which is quite a lot, if we divide this price per watt hour, we get 0.86 lei, which is comparable to these lead acid batteries. I don't know how, because theoretically these lithium iron phosphates should be a lot more expensive, but anyway, this is reality here. Now, if we take a look at lithium-ion or lithium polymer, then we basically look at something completely different. If we take a look at some more serious vendors that are known to sell, you know, genuine accumulators, not secondhand, not cheap replicas, And if we take a look at some of the cheapest accumulators per unit of energy, we might have from Tmue, from this Polish distributor, LG Chemicon model, this one, or Samsung CDI model, this one. The LG has 2.6 amp hours, the Samsung has 5 amp hours. Considering their prices, they are in the range of 2.6 lei to 3.1 lei per watt hour. Okay, so around 50 cents to 60-70 cents per watt hour, something like that. And I do not know, but I'm willing to believe that this particular online shop from my country sells genuine Panasonic accumulators. I have found that these ones that have 3.2 amp hours at this price, these are the absolute cheapest brand new lithium-ion accumulators at the price of 2.1 lei per watt hour, so just a little over 40 cents per watt hour. So for brand new accumulators, you really seem, at this point in time, you seem to not be able to get any cheaper than this. However, I did find ones that were a lot cheaper and some that were more expensive, or even a lot more expensive, but that was before I actually did all of these calculations, before I accumulated all of this experience. So I bought a whole bunch of really questionable accumulators that turned out to be secondhand from all sorts of smaller shops, and I have put them to the test. So this is what I will be presenting to you here in the following minutes. So before I start, let me just show you that I have actually double checked myself. I have bought one of these Chinese electronic loads that are able to also measure the capacity of batteries and accumulators, and I was able to test the device that I have created here with my own hands, and I made sure that he actually performs correct measurements. I have tested my device with this particular electronic load, and as well as testing some real brand new accumulators, 750 milliamp hour accumulators from this well-known distributor that does not sell bullshit. I don't mean to make a commercial or to promote any company that I will show you in this video. I'm just showing you this just to be useful to you. But I have to admit that some of these questionable small companies, they're not questionable just because I say so, but because they choose not to be truthful and not to be honest with the buyers by actually telling them that these are second-hand accumulators, that do not have the full capacity anymore, and so on and so forth. So I have bought from this online shop that is actually a marketplace through which other companies are able to sell. I have bought from a small company that sells with products with this marketplace these sets of 4 accumulators that were supposed to have 8.8 amp hours of capacity, which is insane, and it's a bit difficult to believe that. And I have tested them, and I have shown that I have bought 16 pieces. Okay, I have seen that they range between 2.7 and 3.7 watt hours. In other words, at best they have 1 amp hour. At worst they have, I don't know, 700 milliamp hours. far from being 8.8 amp hours like they said that they should. Okay, and their price ended up being ridiculous, like almost $1 or almost an euro for watt hour of energy. I basically got impaled because, you know, this is actually more than the price that I would have paid for brand new trustworthy accumulators. Anyway, it happens, and this is one of the reasons why I'm making this video, so that perhaps, you know, you learn from my mistakes and you make some calculations beforehand, and you don't trust. Well, truth be told, I bought just a relatively small number of them. I mean, yeah, I bought 16, but they're not all that much, so I haven't lost all that much money. And I was expecting, you know, these to be fake. I just wasn't expecting these to be this fake. Anyhow, moving on. From a completely different shop, I have bought several models. One of this litiu supposedly 5 amp hour accumulators. No, they're not 5 amp hours, but they are above 2 amp hours, so between 8.3 and 9.3 watt hours. Okay, in order to remind you, if you really want to convert watt hours back into amp hours, you divide this number by you divide this number with the nominal voltage, which in this case is 3.7. So if on average these 5 accumulators that I've bought have 8.7 watt hours of capacity, okay, you divide 8.7 by 3.7 volts nominal voltage, and you get about 2.35 amp hours of actual capacity, which is pretty much half of what they say they have. However, considering their price, 1.38 lei per watt hour, that's let me see, 1.38 divided by 5, 27 cents per watt hour. That's not that bad. It's okay ish. This cheap replica of Ultrafire which is Ultra Fleuret, anyhow, says that should have 7.8 amp hours. Far from the truth. They don't even have 1 amp hour. They barely have 500 milliamp hours. I bought 10 pieces of them at 2.35 lei. That's 50 cents per watt hour. Way too expensive, and this is definitely an impale that I received from these guys. Another model that says only 1.2 amp hours, and yes, it's pretty close to that. I got 10 pieces of these between 3.3 and 3.9 watt hours, which means 1.4 lei per watt hour, which is something like 30 cents or so. Okay. Another model of 1.2 amp hours that's a bit worse. So if these had between 3.3 and 3.9 watt hours, these have between 2.3 and 3.3 watt hours. I bought just these 3 pieces. They ended up being 1.72 lei per watt hour. So I don't know, about 40 cents, something like that per watt hour. Depend 8.8 amp hours, which, yeah, needless to say, that's never going to happen. They have around 4.9 watt hours on average, so I would say, I don't know, 1.5 amp hours or so at the price of 1.63 lei per watt hour. Not bad. And I was also curious about these 32,700 model of lithium iron phosphate accumulators that have 6 amp hours, or at least this is what they say they have. Okay, and yes, these ones were actually better in terms of the capacity that they still had, which is, I bought only 2 pieces of these, 13.8 and 14.5 watt hours. So if we are to take, 14.5, let's say that we are doing the average. So divided by 2, that's 14.15 watt hours. If we divide this by 3.2 volts nominal voltage, we get about 4.4 amp hours, which is not bad. It's relatively close to 6 amp hours that they say they have, okay? And the price also seemed to be good, 1.63 lei per watt hour, so one of the cheapest. Now, one of the things that kind of screams that these are, not really brand new is the fact that this particular seller says here unlimited stock. Now, I don't know about you, but this sounds very weird to me whenever I see something like unlimited stock. I'm obviously going to think about, and all of these accumulators, by the way, have this unlimited stock. I'm, needless to say, going to be thinking, how is this possible? Because the only thing that I can think of, the only situation in which you can have an unlimited stock is if for some reason you have some connections to people who basically recover these accumulators from old equipment, from old electronics that people have thrown to the trash, and perhaps some people are recovering them, and like, this is interesting. And it's a bit of an exclamation mark. Another thing that also kind of screams secondhand is the fact that if we measure the voltage right after we have bought the accumulators, if they are brand new accumulators, they will come with a voltage that should be close to the nominal voltage, okay? Accumulators never come full nor completely empty from the factory and from a reputable source. So in this case, for example, I've tested these lithium iron phosphate ones. One accumulator, before I did all the tests that I did and before I charged them, right? One accumulator had 3.33 volts, which is okay, it's normal. So nothing unusual there. The other accumulator, however, had only 0.34 volts. And this is something that clearly tells us that this accumulator is either so old that he discharged himself completely, which is, I don't see that very possible, to be honest with you. I mean, it is possible, but I don't see that very likely. Or this accumulator is actually a second-hand accumulator that has been used and abused by someone else, and now it's being sold to me without actually being told that this is actually a second-hand product, okay? So measuring the nominal voltage of accumulators that we buy from wherever we buy them can definitely tell us something about the state of being of that particular accumulator. So now that I have shown you these things, you know what you need to do in order to establish for yourself what you need to, how you should be discerning between what's worth buying and what's not, and how not to get impaled. And now let's move to final conclusions of this video, okay? So I would say, by looking at this table, okay, we can definitely say that I got impaled in these two particular cases because I bought some accumulators that were overpriced. Even if we make abstraction of the fact that they were second-hand, they were overpriced. They had, they required a lot more money per unit of energy than if I would have bought a brand new accumulator from a reputable source, okay? So yeah, obviously we need to avoid this in the future. However, there are a whole bunch of examples of accumulators that actually have a better price than the brand new accumulators we can buy from those reputable sources. So this tells us that there can be times when it is worth buying these questionable products from questionable, sellers, fully knowing that they are second-hand. I mean, make no mistake, these are second-hand. If we accept doing the work of testing them, of obtaining their real capacity, okay? And if we accept that we basically don't know how much time we will be able to use them, what's going to be their lifetime with us, because they clearly had a lifetime with some other owner, okay, because these are second-hand ones. So there are times when it might be worth paying, I don't know, half on for the same amount of energy on a second-hand accumulator than on a brand new one. Maybe we don't, maybe we're doing something temporary, maybe, I don't know, maybe we're building something that we don't charge and discharge on a daily basis. Maybe we are creating a device that we don't care that much. Well, in that case, sure, we might buy an accumulator from a questionable source, test him, and if we happen to be in one of these situations, yeah, we have actually performed some money savings by, not throwing ourselves at one of those brand new accumulators. If we're talking about litiu accumulators, if we really want the cheapest accumulator possible, then we need to search for the cheapest lead acid accumulator, because there's just no other technology that is as cheap as that one. Okay, so furthermore, let me conclude this video by stating the top 9 conclusions that I can draw from all of this experience. Number 1, we cannot blindly trust any vendor. Okay, there are exceptions if you know for a fact that he's a very big trustworthy vendor, such as Tumue in Europe, Mauser, DigiKey in other parts of the world, or anyway, whatever you know it's really trustworthy in your country. Sure, you might be able to blindly trust that. However, when you're buying from a relatively smaller vendor, you cannot blindly trust him. Okay? For that matter, all accumulators must be tested. At least the ones that came from those questionable vendors. In order to test them, the previously presented tester is worth being built. The tester that I have designed, and you can find on Patreon with all the project files, so you can build him yourself. That one is definitely worth being built. Okay, and after we test the accumulators, we need to calculate the price per watt hour. This is the metric that tells us if that accumulator is worth his money or not. Okay. The 5th conclusion is that most likely the cheap accumulators are either second-hand or rebranded ones, and I'm leaning towards them being second-hand. It's not a big deal as long as we are aware of this, okay? Because they are second-hand, their lifetime is unknown. So we will start using them, but we don't know when their capacity will seriously drop to the point where they will no longer be able to hold any energy whatsoever. That is unknown. It can be in a month, it can be in a year, it can be who knows when. Of course, it also depends on how hard we are using them, how much we are using them, okay? So for short-term applications, possibly even medium-term, it is worth buying second-hand accumulators that have a good price per watt hour. Less than the price of the brand new accumulators. Basically what I have shown you here in this table, that these particular 5 models for me are worth buying more than these brand new ones. Okay. Conclusion number 8: matching of the accumulators is mandatory, and we need to do, especially if we want to place them in parallel. So when it comes to brand new accumulators, we can, I would say for the most part, we can assume that they all have the same capacity, therefore we can just place multiple of them in parallel with no problem. However, because these are second-hand ones or questionable ones, we need to measure their actual capacity, and we cannot place in parallel 2 or more capacitors that don't have the same or very, very close capacity. Okay, we cannot put a 1.7 watt hour in parallel with 3.7 watt hour accumulator, because that would create a problem and would constantly be a problem no matter what. Okay, and the 9th conclusion is that these ones can only be used in applications where their relatively high internal resistance is not a problem. So in other words, when we do not want to draw a high current from these kinds of accumulators, because yeah, they are second hand and they have a relatively high internal resistance, therefore a lower maximum current. If we are okay with this and if we understand everything, then we can definitely work with such products that are questionable, and we can do so in a safe way that, you know, does not impact our wallet, our bank account. So yeah, this is pretty much it. I know it's been a long video, but I consider that this is quite an important piece of information that you need to know in order to not spend more money than you should. That being said, I wish to thank you for watching this video. I hope you found something useful. I also thank the sponsors and the supporters of this project on Patreon. If you want to get all the project files for the accumulator tester that I have mentioned previously, you can do so on my Patreon page, link in the description. Also, once again, happy holidays, and may we all have a better new year than the ones that we have had so far. So once again, thank you very much for watching this video. Looking forward to making yet another interesting video in the near future. So stay tuned. Thanks a lot. Bye bye.